Hi everyone. Today I will present characterizing nanomagnets used for silicon spin qubit operation. Inhomogeneities in nanomagnets are a major problem for development of all devices on the nanoscale. Prominent candidates for high performance, high density memory arrays are spintronic devices that are able to encode non-volatile information in the magnetization direction in an area of a small magnetic volume. This is a problem when we have small grain boundaries or fluctuations of the magnetization on the nanoscale, because this can then in turn impact the operation of the devices. For example, in MRAM, they impact their switching capabilities, and in the racetrack memories, they impact the accuracy of transmitted information. Similar happens also for cobalt nanomagnets for spin qubit control. So here on this image on the right, we can see silicon germanium heterostructure. On their interface, there will be a 2-deck formed, and by applying a voltage on the driving gates, we can deplete the 2-deck and create 2 quantum dots. These 2 quantum dots essentially represent a spin qubit. Now, in order to be able to encode quantum information in the spin qubit, we need to be able to perform reliable rotation. The rotation will occur in the presence of a magnetic gradient of the nanomagnets that are deposited on the top of the device. So in order to obtain a reliable gradient, we need to have carefully fabricated nanomagnets. So there are a couple of requirements. They need to be as close as possible to the spin qubit device, as small as possible, and as efficient as possible. So my talk today will consist of 3 parts. First, I will explain how scanning NV magnetometry works, and then I will move on to 2 examples. First will be magnetic nanowires for high-density memory arrays. Second, magnetic nanowire for spin qubit control. And the question that may naturally arise here is why is scanning NV magnetometry uniquely valuable in the context of these 2 applications? And so the first reason is its spatial resolution that goes down to 50 nanometer. And this is a resolution that would not otherwise be achievable by other conventional techniques. Second is its DC sensitivity, which is 4 microtesla per square root of hertz, which essentially means that if you integrate your measurement for 1 second, you can resolve fields of 4 microtesla. And this can even be boosted to 100 nanotesla. So this allows us to use scanning NV magnetometry as a tool to characterize magnetic and physical properties of different magnetic nanostructures. Further, it also has a small sensor size limited to the atomic radius, so below 1 nanometer, a non-invasive tip, which means that after the interaction of the tip with your magnetic sample, the sample will remain in the same magnetic state. And the third is that it can be operated under ambient conditions, so there is no need to cool down the system. All of this can be, and it has been implemented in Qunami's quantilever all-diamond probe. Now, how does scanning NV magnetometry actually work? So we have this quantilever. On top of it, we have this atomic system. Then if we have a magnetic sample, we can scan over the sample with the tip. And by scanning over the topography of the sample, we can reconstruct the surface magnetic field. The reconstruction of the surface magnetic field depends on the orientation of the magnetic field of the sample with respect to the NV quantization axis. So here there are a couple of different reconstruction points, which I will now skip in order to preserve time. But this is, for example, a nice image of MRAM samples, where you can clearly see that you have a sample that is emanating a magnetic field in space, and by using different orientations of the NV quantization axis, you can reconstruct different field directions. Okay, so now I will move on to this first example of its application to magnetic nanowires for high-density memory storage. So at IMEC, they developed the self-aligned patterning technique in which they deposit cobalt iron boronite films on top of pre-patterned silicon dioxide cores, which have 300 nanometer width, and they're positioned at 600 nanometer pitch. And then they use ion milling techniques to etch away the cobalt iron boronite on top of the cores and in between. And with this, they are left with very, very narrow nanowires of 6 nanometer. So with this technique, they can basically improve the resolution of their nanowires while still keep using the standard lithographic techniques. This allows them to pattern the nanowires over large arrays, and they also have features of fast domain wall propagation and high storage density. So as mentioned previously, the small nanoscopic defects can deteriorate performance of these devices in real life. So people opt to different statistical and microscopic methods to characterize these devices. For instance, in IMEC, they used vibrating sample magnetometry and first-order reversal curves to characterize thousands of nanowires. And these tests have shown that the switching and interaction fields have very narrow distribution, which indicates that the nanowires are more or less the same over thousands of arrays. But then when they had a look with the microscopic characterization technique, such as MFM, again, they saw magnetically homogeneous wires. And now the question that I would like to open is, can we see more with scanning NV magnetometry? But before answering this question, let me walk you through a process of the measurement using ProteusQ. So first we place our sample below the objective, the cantilever, and the microwave antenna. Okay, then at this point, we can start measuring the tip features. So before starting a measurement in our sample, we want to optimize the main parameters of the measurement. So to do that, we will measure the tip properties far away from the sample. So first we perform a quick objective image, then we perform a fluorescence scan, and by using an optimizer function, we track the NV center position. After finding the NV center, we sweep the NV center with microwave radiation at the frequencies correspond to the diamond bandgap, and we collect the ODMR spectra. From the ODMR spectra, we see directly in the software the contrast, the full width half modulation, and the sensitivity. And at this point, we can decide if we need to continue improving our setup or we can just start measuring. For instance, we'll often use, often increase or decrease laser power or micro radiation power. Once we found a satisfying set of parameters for a measurement, we can start approaching the sample by observing the tip on the side view camera. This can be very safely done. So once we land on the sample, we can start measuring. And what we found now, as an answer to my previous question, was that actually we see something new with scanning NV magnetometry. We see feature sizes of 100 nanometer that give small fields of 100 microtesla to 1 millitesla, and this hasn't been observed previously with the MFM. Okay, now I will move on to the second example. This is a project I'm working on as a PhD student in Martina Boyd's group. And so, as I mentioned previously, we want to create reliable gradients to be able to perform rotations of spin qubits. And to fabricate these nanomagnets that we provide the gradient, we used focused electron beam induced deposition technique. And this technique has several advantages comparing to standard lithography techniques. So first, it doesn't require the use of photoresist, liftoff, or etching, which in turn then decreases the probability that you will introduce impurities in your device. Also, it doesn't require thermally provided precursor molecules, but it electrically irradiates the molecules and directly deposits the cobalt structure that you desire. Here on the image in the center, you can see a 6-contact halbar structure with cobalt wires deposited on top, which we fabricated in order to measure the magnetotransport properties of our samples. And for this purpose, we also used MFLI from Zurich Instruments. Further, we also investigated magnetic properties using scanning NV magnetometry. So in this case, we deposited a single wire of cobalt and we simulated the magnetic field of this wire using magnetization saturation of 1.2 10 to the 6 ampere per meter, which then basically for this magnetization saturation, we have a good matching of the simulation and the scans. And this corresponds to 85% of bulk value of cobalt. This value has also been found by EDS and TEM measurements that we performed in our lab. Now, if we have a look at this horizontal wire in the small region, and we observe the upper panel, we apply the magnetic field in the direction of the anisotropy of the wire of 240 millitesla, which is near the saturation field value for the saturation of the whole wire. And we observe that we have a homogeneous stray field above the nanowire with presence of some nanoparticles around. But what happens if we don't apply any field is shown now in the lower panel. And here we see that we have a lot of different nanoparticles and structures that are even present along the nanowire. Even more, if you take a look at the optical micrograph, this is visible as a difference in the material color. And if you have a look now at the fluorescence scan that we made, you see that if we go near to the nanowire, we have the reduction of the fluorescence. The reduction of the fluorescence can occur due to several different effects. First is the material contrast. The second is topological structure that impacts also the scattering of the electrons. And the third is quenching, so the direction of the magnetic field with respect to the quantization axis. So at this point, it's very hard to say what is the cause of the fluorescence decreasing. But after we obtain a magnetometry image, we see also the magnetic field values that are provided by each nanoparticles. Further, we also performed segmentation analysis on the magnetometry image, and we could map that the biggest particles have 100 nanometer size of squares, and they provide magnetic fields up to 3 millitesla. Okay, so now from this magnetometry image, we were able to reconstruct the T2 star times. So first, to explain which T2 star times. So if you have a spin Qubit device and you deposit, for example, this type of nanomagnet on top, what is the decoherence of the spin Qubit caused by the presence of such a nanomagnet? And this is what we calculated here. So by doing several sets of observations, which I will now skip, we reconstruct these contour maps that show that the coherence times would be comparable to the ones that would be provided by EDSR or different mechanisms in standard silicon germanium quantum dots of high quality. And with this, yes, I would like to close the talk. So we've seen a couple of examples of scanning NV magnetometry application on MRAM, racetrack memories, and spin Qubit. And in the end, I would like to thank the whole team in Hunami, my supervisor, Flores Brackman, and our professor, Martino Poggia, and our collaborators at IMEC, Umberto, Rob, and Sebastian. Thank you.